All right, we're going to review all of the BC material. Starting with Unit 10, we started with parametric equations. Parametric equations are expressed in terms of x's and y's in terms of time. It was interesting because we're used to just, x's gives us y's and we plot points on, a two-dimensional axis. I'm not sure what's going on right now. Plot points on a two-dimensional axis like 1, 2, boom, 1, 2. And then, say 2, 3, 2, 3, great. But we would, say connect all of these points, and all we have is just a two-dimensional graph. Well, now we have a two-dimensional graph, but we have another factor in this, in that we have the t's, which expresses the x and y in terms of a time. So at the 0 second, the first second, the second second, we have a position at that moment in time. And all of a sudden what happens is, you have 2, 3, and then you have 4, 2. Well, we start having a direction. So we'd be connecting them in a direction. That's parametric equation. So it's usually x in terms of t's, y's in terms of t's. And the time will give us a position, a two-dimensional position, similar to this, but one extra parameter, being the parametric equations. And we can find derivatives of these parametric equations. They're horizontal tangents, they're vertical tangents, they're slopes of the tangents. So we know that when we want a slope of a tangent, it's dy over dx. Well, if I have x is equal to t's, I would most likely take the derivative of this with respect to t. Let's say I have x of t is equal to, let's just go back to this and say this is 3t and 3t squared, and let's say this is sine t or something like that. Okay, so if I took the derivative of 3t squared, I would probably take it with respect to t. And I would get x prime t is equal to 6t, right? Because the variables would align, we just have 6t. Same with here. If I took the derivative of y of t, I would just get cosine of t. Y of t of sine t is equal to cosine t. Okay, well, dy dx is what I want, but what I have here is actually dx dt, and I have here dy dt. Well, it turns out if I just take dy dt and divide dx dt, so just take the derivative of the y function and the derivative of the x function, what happens is the dt's will cancel, and I'll have dy dx. So if you want to find the slope of a tangent, you just need to take the derivative of the y and divide it by the derivative of x, with both of them being with respect to t. Okay, horizontal tangents and vertical tangents. Remember, a horizontal tangent is when we're not moving up or down, but we are moving left or right with our tangents. So a horizontal tangent wouldn't be when this is equal to 0. Just the top piece equal to 0. Our vertical tangent occurs when just our bottom piece is equal to 0. Okay, so that means I'm moving left and right. I'm not moving left or right, but I am moving up or down. Okay, so when the dx part is 0, that would mean I'm not moving up or down, not moving left or right. And dy equaling 0 is not moving up, down. And it's interesting, based on the sign of this, you can tell what direction you're moving in. If dx dt was positive, that means we are moving right. If dx dt was negative, we're moving left. If dy dt was positive, well, that means the change in y is positive, which means I'm going in the positive direction. I'm going up in that direction. So based on the signs, you can tell whether you're going up, down, left, or right on the direction of your graph just by looking at the derivatives. So keep that in mind. Derivatives can tell you direction. Okay. Now, it's very interesting second derivative, which is how we're going to find concavity. Well, parametric equations have concavity. Now we're used to finding the second derivative being d squared y over dx squared. Well, I have a dy dx right here, which I found by dy dt over dx dt. But if I take the derivative with respect to t of dy dx, and you'll find that, for this, let's say, this derivative, we had cos t over 6t. This is dy dx. If I take this derivative, it would be with respect to t, because I just have t's. So when I take the derivative with respect to t, I get d squared y over dt dx. So we have a situation where the derivative of my first derivative, my horizontal tangent, doesn't give me my second derivative. But watch what happens if I divide this by dx dt. You'll end up with d squared y over dt dx times dt over dx. The dt's cancel and the dx's become squared. So if I want to take the derivative to find the second derivative of parametric equations, you would take the derivative of your dy dx, your first derivative, but then divide by dx dt. That's a very important concept. So if we went to the previous one, I had cos t over 6t. I would take the derivative with respect to t of cos t over 6t, but then I would make sure I divide it by dx dt, and we found dx dt was 6t. Okay, so take the derivative of that, divide it by dx dt. I'd have to use the quotient rule to take this derivative and then divide it by dx dt. So this is a common question asked on the BC exam, the second derivative of parametric equations, and students often forget it's this special second derivative. Okay, so concentrate on that. Take your your derivative of your first derivative, which is dy dt over dx dt, divide that by dx dt. 2D motion and rest, we talked about going up or down. This is dy dt is positive. This would be when dy dt is negative. If I'm going to the right, dx dt would be positive. And if I'm going to the left, dx dt would be negative. Okay, that's some motion. We could also talk about my velocity. So if my position is given by x of t, y of t, sometimes it'll be given in terms of, in vector form. Now, position's not necessarily a vector. Position is just where you're going. But just like with straight line motion, if I took the derivative and I got x prime of t and y prime of t, all of a sudden I would have a velocity vector. This would be like a direction and a magnitude and a direction. And if I want an acceleration vector, I would take the second derivative. And sometimes you'll see it in this vector form, which is using these brackets instead of parentheses, because it's a vector. It has direction and magnitude. If you are at rest, that means your velocity is equal to 0. Well, that means I can't be moving up or down or left or right all at the same time. So that means x prime has to equal 0 and y prime has to equal 0. You'll see some problems where they say, when is your velocity at rest? You have to set both your x prime equal to 0 and your y prime equal to 0. What else? We talked about velocity. We got that. We got acceleration. Let's talk about speed. Speed is the magnitude of velocity. So it's velocity without direction. Typically, velocity can be looked at in terms of a vector. Oh, at this point in my graph, I am going in this direction at this magnitude. Well, the magnitude can be discovered using the Pythagorean theorem. Speed would just be equal to, we use the absolute value for magnitude of velocity, and that would be equal to the square root of whatever this dx dt is, squared, plus the dy dt squared. And this is just a Pythagorean theorem formula, and this would be speed. This is just the magnitude. Notice there's no integral for speed. It's just Pythagorean theorem. This would be my dx dt portion. This would be my dy dt portion. And we can find this distance here using that. And then finally, arc length. this is a common question involved in the BC exam. If we have an arc length and we want to try to figure out how much distance this arc is, well, if I zoomed in at a specific point, what I would find is that we'd have a straight line. You know, we kind of linearize our functions when we zoom in. Say we zoom in here and I see this. Well, to find, you know, this distance of this very teeny tiny piece, I'm going to say it's a tiny zoomed in piece. We know that it has some change in x. We'll call it a dx, an instantaneous change in x, and an instantaneous change in y. We'll call that dy. Well, I'm just going to take an infinite sum, and I'm not going to designate where I'm going from and ending, but we'll just assume this is the infinite sum, the integral, of my dx squared plus my dy squared, square rooted Pythagorean theorem. So all of a sudden, this would be my formula for the arc length. Now, it all depends on what type of function we have that kind of manipulates this to what we want. Say we have some function that is a parametric equation, So it's got x of t's and y's of t's. Well, these are expressed in terms of t's, so this would probably be some point when t is equal to, say, 0, and this is some point when t is equal to 2. So it looks like I need dt here if I have stuff expressed in terms of t's. Well, to just give it a dt, I'm going to multiply by dt over dt. And all of a sudden, we'll create our arc length of our parametric curve. Okay, now I'm going to throw this dt underneath the square root, but when I throw it underneath the square root, it needs to turn into dt squared. And it would be essentially like multiplying all of this stuff by 1 over dt squared. And what we can do is then put the dt squared underneath both of these and distribute it. And we can then, since I'll have a dt on the outside, go from one t to the other t. So in this case, in the previous one, it'd be 0 to 2 of the integral of dx dt quantity squared plus dy dt quantity squared. So this would be the formula for the arc length of a parametric curve. Just comes from an infinite sum of dx squared plus dy squared, Pythagorean theorem. Now, it's interesting if we have a function, f of x, or a y equals f of x, and we want to find the arc length. Well, again, let's start out with our, our formula for the conceptual formula for arc length, just dx squared plus dy squared. Well, now if I had a function, it would typically be between two x values, say 1 and 4. And I would have a dx here out there. Well, to have a dx, I need a dx down there. So I just multiply it in, dx over dx. Well, let's put this underneath the square root. That would turn into 1 over dx squared. And now if I distribute that 1 over dx squared, watch what happens. I'd have the dx on the outside. This would be dx over dx squared, and this would be dy over dx squared. Well, dx over dx is just 1, and dy over dx is just the derivative, or f prime. So if I have the arc length of a function, we can go from an x value to an x value of the square root of 1 plus dy dx quantity squared with respect to x. And now I would use x's here and here, or in the example above from 1 to 4. Okay, so arc length, all coming from taking infinite sums of, very, very teeny tiny straight lines that have a dx part and a dy part, and then manipulating it to use the integral with specific values, multiplying by dt over dt, multiplying by dx over dx, giving you this. Okay, so that was parametric equations. Pretty simple stuff. Hopefully you'll see lots of that. Then we got into Unit 11, which is antiderivative techniques and polar equations. People don't love polar equations, but we will go over it. Antiderivatives by parts. This is the first thing we'll talk about. So if I want to take an antiderivative and all of a sudden I see we have, multiple things like x e to the x. And I try use substitution and it doesn't work. Well, let's recall that if I want to take the antiderivative of some u dv, I can actually rewrite this as u times v minus the antiderivative of v du. Okay, this is just found out using the product rule, and this helps us, find antiderivatives of things like this. Now, it's very important to understand that we need to rewrite this, and this integral needs to be easy to take. Now, there are rules to helping decide what is going to be the u part of your antiderivative and what is the dv part. We usually say it's late, which means L is logs. If you ever see a log in an integral being multiplied by something like that, this is what we will select u to be. So that means the rest would be dv. If I don't see logs, but I see some algebraic stuff like x to a power, well, I'll then pick that. Then we would pick trigs before we would pick an exponential. Okay, so exponential is usually the dv. Logs and x's are usually our u's. So in this situation, x e to the x, I'd set u equal to x. dv would equal e to the x. Here, du would equal 1. V would equal e to the x. I would rewrite this as uv minus the antiderivative of v du. V is e to the x, du is 1. Technically, we should have the dx here and this dx here, and when we take the antiderivative of this, it would just go away. When I took the derivative of this, it would become dx. But now I can take the antiderivative of this, e to the x. So antiderivative of e to the x would be e to the x, and then I include a plus c. Now, other types of things you'll see, let's say we have x cubed log x. Well, here people like to set u equal to x cubed and dv equal to log x, but don't do that. That's not going to help you. If you see that, we would use late. Logs would be selected first as our u's. So I'd select log x. dv would be x cubed. du would be 1 over x. V would be 1/4 x to the 4th. And then I would rewrite this as uv. That'd be 1/4 x to the 4th log x. That's vu, but uv minus the antiderivative of v du. Now this is where picking logs work, because the derivative of log is 1 over x. That 1 over x will cancel and make this an x cubed. So that's fantastic. So I have 1/4 x to the 4th log x minus, this would be x to the 4th times 1/16 plus a c. Okay, so those are examples of antiderivatives parts. Antiderivatives by partial fractions. If I have some antiderivative, let's say, back to this. Recall if I had something like this where I'm trying to find the area, well, we would make sure we found the change here and the change here. Okay, really quickly, if we did that, we could do it either in multiple parts or in one part. But it's to find the exact area, make sure you're finding the change in both uv and the antiderivative of v du. Good. Now, antiderivatives by partial fractions. If I have something like, let's make an easy one. And I want to find the antiderivative of this. The goal is to rewrite this based on what its factored form is. We know that this can be written as some value over x plus 2 plus some value over x plus 1. Why did I pick x plus 2 and x plus 1? Because this can be factored to be x plus 2 times x plus 1. Okay, so we start with that. The next thing we want to do is to multiply everything by this denominator. So I'm going to multiply everything by x plus 2 times x plus 1, including over here. Well, on this left side, everything would cancel and just leave us with 1. On the right side, the x plus 2's would cancel, leaving us with a times x plus 1. And here, this would be b times x plus 2. Well, this is the situation where we have an equation and we want to solve for a and b, and we'll pick some x values to help us. So we'll select x equals -1. Well, that would give me, this would go away. This would just be b times 1, so I get b is 1. Now let's select x is -2. I'd get 1 is equal to a times -1 plus, this would be 0 because this would go away. So this would give me that a is -1. So after I find that, turns out I could say, all right, well, let's go back up here. I know that 1 over x squared plus 3x plus 2 could be written as negative 1 over x plus 2 plus 1 over x plus 1. I can then take the antiderivative of both of these because it's what we call the partial fraction decomposition of this. And I take these separately. The antiderivative of negative 1 over x plus 2 would be negative log absolute x plus 2. The antiderivative of 1 over x plus 1 would be log absolute x plus 1. And then let's recall some log rules. If I have, a constant in front of a log, I can rewrite this as log of this to the power, to the constant's power. So that's one thing. Other log rules, if I'm adding things, it's the same as taking one log and multiplying it together. These all come from exponent properties. And the final one, if we are subtracting things, log x minus log y, this would be the log of x minus over y. Here, this is the log of x plus 1 minus the log of x plus 2. You can either say this is x plus 2 to the negative first, which is 1 over x plus 2, and then you can multiply it. Either way, you can figure out that this is log of x plus 1 over x plus 2 plus a c. Okay, so that would be a way to take the antiderivative of this, and we got it. So that's partial fractions. Finally, improper integrals. Now, if you're asked what is, say, this guy, okay, well, let's see if we can find it. Now, typically, if you were to do a free response problem, step one would be to write this as a limit. If you did not write this as a limit, it would technically be incorrect. You would have to use this limit notation if you're doing this on a free response. If you're not doing it on the free response, just go ahead and do what you normally do when you see integrals, is take the antiderivative and substitute in. So this is an improper integral because we're going from 1 to infinity. Also recall, improper integrals could be if you're taking an integral over something that has a vertical asymptote. So here, this function between negative 2 and 1, this had a vertical asymptote. So if you're trying to find, the area, you would see that most likely it would be non-existent. It would not be able to be taken. Some will be able to do. Look at some problems on the multiple choice packet to help. So here we have 1 to b of x squared, 1 over x squared. I would write this as x to the negative second. The antiderivative of that would be negative 1 over x. This would be x to the negative first times negative 1, so negative 1 over x. And I'd find that change from 1 and b, and I'd get negative 1 over b minus negative 1 over 1. Now, if I plug in infinity for b, we know this would approach 0, and then turns out this would approach just 1. So this, though, if you think about it conceptually, we're talking about finding an infinite amount of area because we're traveling towards infinity. But since this function gets closer and closer to 0, we find that we converge towards a number, and we will not have an infinite amount of area. That's the key concept that we move into Unit 12 about, infinite sums of things in series. So that's an improper integral. Make sure you use a limit if it's free response. Make sure you understand, as something approaches infinity, what's going to happen. Now, if this was 1 over x, watch what happens. We'd have 1 over x. The antiderivative of 1 over x would be log x. And then we'd have log of b minus log of 1. Well, in this situation, we should remember that this grows. So this would be approaching infinity. Log of 1 is 0, so this would approach infinity. When we say something is approaching infinity, we would say it would diverge. Okay, so that's improper integrals. Now let's talk about polar graphs. Just a couple quick things to remember about polar graphs. In your calculator, you can graph polar graphs if you switch the mode. So remember, you can go to mode, down here to polar, and then when you go into y equals, it becomes an r equals. Typically, with polar graphs, we will graph r equals some stuff with thetas. Okay, r is our distance from the origin, and theta is the angle. So this point would be, maybe 3 comma pi over 4. Okay, because it's a distance of 3 and this angle is pi over 4. And in your calculator, you can find, say 3 cos 3 theta. Some cool looking graphs of petals. Let's zoom standard. Actually, let's go to 8 cos 3 theta. That'll look a little bit bigger. Okay, good. So now we have this graph, and polar graphs make some interesting things. Now, it's very important that, if you press trace, it's all about the theta that produces your x and y. So we're starting with an angle of 0. My graph of 8 cos 3 theta would start at 8 comma 0 on a coordinate plane, but really it's 0 comma 8 or 8 comma 0. That would be the start. 8 would be the radius when my theta is 0. And then as I'm plugging in different theta values, we produce different r values. So your calculator doesn't give you the r's. It just immediately changes them to x's and y's. And you can see how right now theta at 0.52, this is actually at pi over 6 units. And then as I'm plugging in values, my theta is actually over here. So theta started 0 and then theta got up here. But when theta's up here, my r ends up being negative. So here, this would be when theta is 0.7853, r would be negative, whatever this distance is. Okay? Then as I go all the way up to theta equals pi over 2, I'm back at 0. And then if I go, I'm now in the second quadrant with my theta values. And if I get to theta is equal to pi, I'm back at 0. And actually a little bit further, I'm not at 0 yet. As I get to past the value, all of a sudden, I'm still in this second quadrant, and when I get to pi, I've completed my graph. Notice pi 3.141592. So this entire graph is created from theta 0 to pi. And this is important to know that it's created from 0 to pi and not 0 to 2 pi. Now, when you are graphing, your calculator automatically goes from 0 to 2 pi. And what you can do is over here, you can change this to graphing with a circle to show how the graph is created from 0 to 2 pi. See how it's going over itself again. So it was created from 0 to pi, and then from pi to 2 pi, it just retraces itself. That's very, very important concept to keep in mind when we are finding the area inside these polar graphs. Now, it's very important that these points, though this is a r and a theta, can be converted to x and y coordinates. It's a very important conversion. Using trigonometry, we could say the x coordinate is just going to be r cosine theta. This comes from the whole cosine of theta is equal to adjacent over my hypotenuse. Well, adjacent we would say is our x coordinate. The hypotenuse is our r coordinate. So multiply by r, you get r is equal to, x is equal to r cosine theta. So this x coordinate would be 3 cosine pi over 4. Cosine pi 4 root 2 over 2, so this would be 3 root 2 over 2 for an x coordinate. Now, also, the y coordinate could be said as r sine theta, knowing that sine is equal to the opposite side over the hypotenuse. The hypotenuse would be r in this case. This is extremely important to know that you can convert, really, polar graphs into parametric equations using this relationship. And if you wanted to find tangents of polar graphs, well, again, you want to find dy dx, you would have to convert to y and x, because this would be in terms of thetas and this would be in terms of thetas. When you took the derivative of this would be respect to theta, this would give you dy d theta. So how quickly your y's are changing in a specific moment in time. If you took the derivative of this, this would give you dx d theta, how quickly your x is moving at a specific moment in time. So the tangents of polar graphs are going to be that dy d theta divided by the dx d theta. That would be the only way you would find the tangent of the polar graph. Okay, take the derivative of the y. Remember that y is r sine theta and x is r cos theta. Okay. Now, area inside polar graphs, what we end up doing is we take, our polar curve and we'll split it into little teeny tiny pizza slices. Now, this ends up being kind of like an arc of a circle with this teeny tiny pizza slice. And now the area of an arc is, well, pi r squared is the area of a circle, but we're just taking a portion of it. So I'm going to say times theta over 2 pi, knowing 2 pi is an entire circle. Theta would be my angle at which I am talking about. So here would be my angle here, and here's my arc of my circle, pi r squared theta over 2 pi. Now, as these pizza slices get smaller and smaller and smaller, theta gets smaller and smaller and smaller until it becomes d theta. And what we're going to do is we're going to take an infinite sum of these pi r squared times theta over 2 pi, but notice the the pi's will cancel, and the theta would turn into d theta, and we end up with this formula of 1/2 r squared d theta. Notice how it just comes from pi r squared times theta over 2 pi. This is easy to remember if you recall this. Now this would be from some theta to a second theta. Okay, so let's say we want to find the area inside all 3 petals of 8 cosine 3 theta. Well, you would think, okay, let's just go from, starting from 0, it would be 1/2 r 8 cos 3 theta squared d theta. But a lot of people mess up on this. Okay, when we look at the graph of 8 cos 3 theta, a lot of students always assume we're going from 0 to 2 pi. But in this situation, I'm just going from 0 to pi, because that would be around the curve once. If I went from 0 to 2 pi, that would be multiple parts of my area. Okay, so 0 to pi. You could have also found another 0 and, found just one petal. Well, if you found that this 0 is at pi over 6, you could have gone and for one petal just do double 0 from pi over 6 of 1/2 8 cos 3 theta squared. And this would be the area of one petal. And that's just one way to find one petal. You go from negative pi over 6 to pi over 6, that would create one petal. Or you go from 0 to pi over 6 and multiply it by 2. Okay, that would be the basics of area. Also, optimization of polar graphs. Let's say we want the, when is r furthest away, or when's the polar graph, say we have a polar graph like this, when are we furthest away? So typically you want to find a max for r. That's very important to understand that maxes for r could be at absolute maxes or absolute mins. Because when r is negative, let's say when theta is over here, I'd produce this point. Well, this would be a negative r. That would still be a positive distance away from the origin. So if I want to find the max r, or the max distance from origin, you'd find the max and the min r, and then compare those lengths. Also check your endpoints, obviously. And we should know to find a max or a min of something, take the derivative, set it equal to 0. Okay? So just recall that. If you want to find the max r, understand that it could be at a negative r. Moving on. Series of constants. We're just taking infinite sums of, numbers. Does this equal something? If it goes on forever and ever. Or will it just approach infinity? It's an infinite sum, right? You would assume that approaches infinity, but just like we saw with areas, you do take an infinite sum and we decrease in our values, sometimes that will approach a specific value. It'll get closer and closer to a specific value. Now, the most important thing about series, stuff when being added, is that if your limits of your terms, and typically we'll call these terms A1, A2, A3, and this would be the sum of my AN, and starting from 1 and going to infinity. If my ANs do not approach 0, well, then we know immediately we are going to diverge. This is the nth term test. The nth term test means If all of a sudden, I go and I get closer and closer to 1/2, so I got 1 plus 2/3 plus 3/5 plus 4. I'm just making this up. I'm thinking I'm getting closer to 1/2. I might be 4/7, 5/9. You're getting closer and closer to 1/2. Well, eventually you just be adding 1/2 each time. If I'm adding 1/2 each time, I'm not going to be adding smaller and smaller values. I'm going to diverge. So remember that your nth term must be approaching 0 for you to possibly converge. It's not always going to be the truth. It will be a possibility. Okay, geometric series is one of the first series we examined. That's typically when we have some r value being taken to the nth power. Sometimes it's multiplied by some other constant. N could start at 0, could start at 1. It doesn't really matter. Okay, this would converge if the absolute value of r is less than 1. Okay, so it's got to be less than 1. If it's greater than 1, then it diverges. And it would diverge if it's greater than 1 because it wouldn't pass the nth term test. Okay, now geometric series are great because we could actually find the sum. The sum of a geometric series is always going to be the first term divided by 1 minus the r. Okay, this can be shown once we looked at Maclaurin and Taylor series that its sum is that. A p-series. P-series are typically look like this. Usually it starts from 1. It's 1 over n to the p. This was r to the n. Here n is in the kind of base and p is the power. This would converge when p is greater than 1. This is going to diverge if p is less than 1 or equal to 1. When p is equal to 1, we have this famous series, which is 1 plus 1/2 plus 1/3, etc., etc., etc. This is the harmonic series. The harmonic series is a divergent series. You can just say it's divergent because it's the harmonic series. We know kind of like the definition of a harmonic series, and on the AP exam, you could say, oh, this is the harmonic series, it's divergent. You don't have to use a test to show that it's divergent. A way that you can show that the harmonic series is divergent is using the integral test. Integral test says if this integral of a sub n, just written as some function, if this equals a number, then we say we converge. If this is going to approach infinity, we'll diverge. Sometimes you will have to use the integral test based on the function. I'll just quickly show you, and we already did this. If you had 1 over x, we know this is log x from 1 to infinity, and this is divergent. So that just kind of confirms that the harmonic series, infinite sum of 1 over n, will diverge. The direct comparison test, this is important. So when we have a series and we know that this series, say, diverges. So this may be the partial sums So let's say the partial sums are going to approach a value. So it's important to know if you are given, that the partial sum is equal to some function, you want to find the sum of the series, you can just take the limit as n approaches infinity of the partial sum. Sometimes you'll have questions of, here's an expression for the partial sum. Sn is equal to 3n over 4n plus 2. And they say, what is the sum of the series whose partial sum is given to you by this? Well, just find the limit as n approaches infinity, and you'll see that your partial sums will approach 3/4. So that's got to be your sum of your series. So here our partial sums are approaching 3/4. That's good. Now, if I know I have a series that all of the terms are less than it, well, then all of the partial sums would end up being less than these partial sums. We would have a convergent series. So let's say that this is called A sub n, and this is the partial sums, and this is B sub n. If we know A sub n converges, and B sub n is less than A sub n, we know B sub n's got to converge. However, if we have another series that is greater, well, we don't know if it's going to converge or diverge. Let's say this is some C sub n. Well, if A sub n is less than C sub n, here I have no idea if that's going to converge or diverge. It's only converging series. If you're less than the converging series, you're also going to converge. Now, with this, if, say, C sub n diverges, again, since C sub n diverges, if we are greater than C sub n with some other function, we know this is going to also diverge. Just saying, taking C sub n, let's say C sub n diverges, and we know another one, D sub n is greater all the way around. Well, if you're greater than that and you're greater than a diverging series, you're also going to diverge. However, if B sub n is less than C sub n, I wouldn't know what's going on there. Okay, so that's a direct comparison test, usually asked in multiple choice questions, just like coming right out and using it. Typically, comparison tests that we use are limit comparison tests, and limit comparison tests are great. Turns out, if you look at the limit as n approaches infinity of two different series, if it equals a positive number, then you could say either they both converge or they both diverge. Now, typically what we would do is we'd be asked, hey, let's say A sub n is, 3n over 4n cubed plus 2. And you're like, hey, does this converge or diverge? Well, typically what we do is we pick a good comparison to this by looking at the limit as n approaches infinity of this. I would kind of cancel out the 2, the n's would cancel, the 3/4 kind of wouldn't matter, but I would typically compare this to 1 over n squared. And then I would look at the limits as n approaches infinity of a over b. So I'd have 3n over 4n cubed plus 2 divided by b is the same as times n squared over 1. Now, I know that this would be 3n cubed. And if I look at the limit as n approaches infinity, this would cancel. The n cubes would end up canceling, and I would get 3/4. And I'd say, yeah, that's a positive constant. So now, either both of these converge or both of these diverge. Well, we should know that this is a p series with p greater than 1. Since p is greater than 1, this converges. Since this converges, this is also going to converge. So this is how we use the limit comparison test. This is the easiest one for crazy ones that you don't necessarily know. Finally, the ratio test. The ratio test is a great test. It just is kind of similar to the geometric test, where we know if we know what we're multiplying each term by, as long as it's less than 1, we know that this is going to converge. Well, it turns out if we just look at the terms as we go towards infinity, the next term divided by the previous term, as long as that's less than 1, as we're approaching infinity, we are going to converge. This is super important because we can actually use this for a lot of different series with x's to figure out what values x needs to be for a series to converge. Take, x minus 4 to the n over n squared, this sum as n approaches infinity, or as n approaches infinity and starts at 1. What values is x so that this converges? Well, you'd actually use this ratio test you'd plug in n plus 1 and n, you'd divide the two, you would then be able to set up, you know, an absolute value of something being less than 1, and you can find the values that x has to be between. Okay, this is, let's say, put a 3 here. This is a very common problem. I'm not going to show you the old problem because they actually take a while, but go and watch the ratio test to kind of figure out if you don't remember that. Okay, but it's important. It's the absolute value of the next term divided by the previous term has to be less than 1. Alternating series are super easy. If your series alternates, so that means it's, you know, plus 1 minus something, plus something, minus something. Et cetera, et cetera, et cetera. And if the terms are going to approach 0, well, then you know you're going to converge. It's incredible that all you need is that. Do you alternate? Do your terms approach 0? Is the next term smaller than the previous term? Like that, then you're going to converge. It's not necessarily the terms approach 0, but the next term has to be less than the previous term always. Because when this happens and we look at the partial sums, you'll see that we'll start here and then we'll bounce down. But then we're going to add something, but it's less. But then we're going to subtract something that's less. And we'll add something that's less. And subtract something like that, less. And you can see by looking at the partial sums that you are going to be straddling, which each addition and subtraction, the actual partial sum. And this helps with our error with alternating series, which we'll talk about. That our error, like the distance between our partial sum and the actual value, is always less than however much I add or subtract to get to the next term. Always going to be less than. So that helps understand. Radius and interval of convergence will come from using the ratio test. If I end up with something like x, absolute x has to be less than 3, this is what we would consider a radius of convergence. If it was x minus 2 is less than 3, that's still the radius of convergence. The interval of convergence, typically we would then set this equal to that to get rid of the absolute value. And then we'd say x has to be less than 5 or less than negative 1. Now, it's very important. The ratio test says we will converge absolutely. Okay, so absolute convergence and conditional convergence we need to talk about. Absolute convergence means the absolute value of your thing will converge. But conditional convergence is also convergence. When we ever do the ratio test and we find an interval of convergence, we need to make sure we check our endpoints. So typically we'll just plug in the value 5 and negative 1 into our series. We'll then examine the series and see if it converges at that endpoint or does not converge at the endpoint. Okay, make sure we check our endpoints for our interval of convergence. Okay, and typically we are using the ratio test to find that. Sometimes you might see a geometric series and then you know it'll converge if you're less than 1. So different things, but typically using the ratio test. Okay. Taylor and Maclaurin polynomials. It's very simple. It's just a really great way to approximate a function as long as you know some derivatives and a point. Okay, so typically we call a Taylor polynomial as an nth degree. So p sub 3 would be a third degree. And if you had p sub 3, you'd end up with an x to the third power. But this nth degree Taylor polynomial is always just a point of our function that we're trying to approximate. So we got a point. We make sure the point of the function and the polynomial agree. Then we make sure the derivative at that location agrees. But we need some little bit extra. We need this x minus c so that when I plug in c, I still have the point that agrees. And then I end up with the second derivative has to agree. So the second derivative has to agree. But I still need to make sure when I plug in c, I have f of c and not some other extra stuff. So I end up with an x minus c squared, but then I need to divide that by 2 so that when I take the derivatives, it all works out. Then when I get to the third one, I need to make sure that agrees. But I end up don't just needing 3, I end up needing 3 factorial. And this ends up being 2 factorial. And as I continue to go on, I just add extra derivatives, x minus c to the 4th power, and with these factorials. The factorials are needed so that this agrees with my function, this agrees with my function, this agrees with my function. We've kind of walked through that within the lesson. This is a Taylor polynomial. A Maclaurin polynomial is a special Taylor polynomial. Maclaurin polynomial is when c is equal to 0. So Maclaurin polynomial would be f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial, et cetera, et cetera, et cetera. Now, so if I wanted p sub 3, I would just have 1, 2, 3, 4 terms, as long as I have the x to the 3rd power in it. But I would need the terms before it until I got to the x to the 3rd power. That's very important. Now, when we talk about error and Lagrange's error, it's very important. Lagrange said, let's say we had that 3rd degree Taylor polynomial for x. And let's say it is equal to this, 1 plus 2x, and this is centered at x equals 1. So f of 1 is 1, x minus 1. Then I'd say maybe the second derivative would be 3x minus 1 squared. Notice I'm using 1 here for c. And then my 3rd degree, let's say the next derivative would be that. And there's my 3rd degree Taylor polynomial. Now this approximates f of x around x equals 1. Well, Lagrange found that if I took this 3rd degree Taylor polynomial and added a remainder, I would get the exact value of f of x around x equals 1. And he discovered what r could be. He discovered r is just the next term of the Taylor polynomial. It would be the 5th term with the 4th power. So he said, okay, r has got to be the x minus the c to the next power over the next, powers factorial. And he found that the next derivative had to be some special value between what you have and what you're trying to approximate. And this would be r. Now, this is fascinating because to find out, the max distance, we would call this our error. To find the max error, we would just find this max derivative of this term. And depending on what you're approximating and what you're centering around, you would have that. So in this case, since I have a 3rd degree Taylor polynomial, Lagrange says, well, there's going to be some 4th derivative at some value. This value is between 1 and whatever you're approximating. Let's say we're approximating 1.5, so f of 1.5. So this z value is between 1 and 1.5. This would be 1.5 minus 1. This would be the next term, so 4. This would be 4. And we'd be able to find, this value exists. But if I wanted to find a max, it's very simple. You would just find the max derivative between 1 and 1.5, the 4th derivative, times 1.5 minus 1, so that's 0.5, to the 4th power all over 4 factorial. And typically, this will either be given to you or you can find it using a graph. Now, those are polynomials, which means they had a finite number of terms. They stopped eventually. This would be a 4th degree Taylor polynomial. The 3rd degree would just stop at the 3rd term. Well, if we talked about series, this would be when we went on for infinity. So we would just continue to add the next term and the next term. So it'd be your sum, starting from 1 and going to infinity, of your f of c derivatives times x minus c to the nth power all over n factorial. and this would be 0. Okay, so it goes on to infinity. We have just an infinite amount of terms. And we found through the convergence of some of these power series that the Taylor-Maclaurin, the Maclaurin polynomials for e to the x, which we can find, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, et cetera, et cetera, et cetera. Turns out this, as long as we look at an infinite amount of terms, is actually convergent towards the actual value of e to the x. They're equal to each other, okay? As long as we have an infinite amount of terms. They're equivalent. This is what your calculator uses to approximate e to the x values. It's the same for cosine and sine. It's actually equivalent to these Maclaurin polynomials. Now notice Maclaurin because it's not x minus c, it's x minus 0. So cosine ends up being 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And these you have to know. And sine is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. You can discover these ways to remember which one is which. Think about f of 0, cosine of 0 is 1. Then f prime would be sine of 0 is 0. Then f double prime gives us my x squared. F double prime would be negative cosine. That's why I have a negative here. Sine of 0 is 0, so that's why I don't have a f of 0 term. I start with my x term, because the derivative of sine is cosine. Cosine of 0 is 1. Last one is 1 over 1 minus x. Coming from the geometric series is 1 plus x squared plus x cubed, et cetera, et cetera, et cetera. Okay? Now, it's important. Compositions of Taylor or Maclaurin series, if, say, you're asked what does e to the 3x equal to, well, we know that f of x, which equals e to the x, is 1 plus x squared over 2 factorial plus et cetera, et cetera, et cetera. Well, if I want f of 3x, I would just need to plug in 3x wherever I saw x. And this is how you can kind of figure out what these are equivalent to. Okay, just plug in 3x everywhere. This goes for, what does the derivative of e to the 3x look like? Well, once we have e to the 3x, take the derivative. The 1 would go away. This would be 3. This is 9x squared over 2 factorial. So that's 9 over 2 times x squared. Take the derivative. That would be 9x. And then you would just keep going and keep going and keep going. Okay? So that would be compositions that can be done for any of these. And that's pretty much it. It's very brief overview. Euler's method and logistic differential equations. I won't do a quick overview because it was really just one lesson. It's quick lessons. Watch that lesson, and that is your review of your BC material. Hope this helps with a quick overview of everything.